Hello and welcome back to data analysis for the humanities, and we talk about functions now and how to visualize functions in Python. There is a whole course about that on this channel where I explain to you how to use Python and how to use matplotlib to visualize functions. So I will not do all of this again now. We will just look at one piece of code very quickly, and then you will see how it's done and hopefully remember it. And if you need more introduction than this, then please go back and watch the other video, which I will put somewhere here and in the description so that you can easily find it. So here's the code how we visualize functions. We use a library called matplotlib, which is imported here as PLT. Importing as PLT means that you just give it an alias, another name. So instead of having to write matplotlib every time, you just write PLT. PLT is just a random piece of 3 letters. You could use any name for it. You could call it Peter or John if you wanted. PLT is just usually used for some historical reason. So now we want to create a range of input values that we will use to show our function. You remember a function maps input to output values, and often in these machine learning contexts we use input values from 0 to 1, normalized. They are called normalized inputs because you have all sorts of inputs, right? You have percentages from 0 to 100, and perhaps you have voltages, for example, in a USB port from -5 to +5 volt, and you have voltages in a lamp standing on your desk from 0 to 220 volt or 110, depending on where you are. So all these are different ranges, and when you want to process them in Python mathematically, it's often good to just say we normalize them to the range of 0 to 1. So all my probability, 0 means zero probability, 1 means 100%. 0 means no electricity on my port, and 1 means 5 volt electricity on my port, or 110 volt of electricity on my plug, on my socket. So this is then easier to process because we don't have to care about the particular numbers in our program. We just process everything as if it was between 0 and 1, and we have to map it before we start the program, and then we have to unmap it back and map it back again to its real value after the program is finished. But our program can be agnostic, right, about the ranges of values in reality, because we just deal with 0 and 1, the range of 0 to 1. Okay, so this is what we want to do here. We want a range of inputs between 0 and 1. In this case, we even want to have -5 to 5 for some reason. This example now works at -5 to 5. And we want to create this so that we have -5 and -4.9 and -4.8, -4.7, and then we go until 4.8, 4.9, 5. This is the range we want to create. And the problem is in Python now, we have a range function that would do exactly that. But this range function can create only integer values, only full numbers. It cannot create decimal numbers, floating point numbers. But we want floating point numbers. So we want to make a list of these numbers, but we don't have a function to create them easily. We could use a while loop, but it's easier to do the following, what is done here in this code. We create a range that is 10 times what we want. We start at -50 and go to +51. Now, if you wonder why it's 51 on this side, because you remember in most Python ranges, functions, you always start including the left side and excluding the right side. So also when you make a slice of a list or something, or here in range, the last value is not reached normally. So if I say -50 to 51, in reality I will get values from -50 included to +50 included, 51 excluded. So this is why we go to 51. And now we will get full numbers, because this is what range does. It gives me full numbers, but then I append to my input array not the number itself, I append the number divided by 10. And so when I get, let's say, 2 divided by 10, 0.2. I get 20 divided by 10, 2. And so in this way, I go from a range of -5 to +5, which is exactly what I want, in 0.1 steps, using range, which actually cannot do this, but we can trick it into doing this by dividing by 10. And whatever range you have, you can create in this way. So if you wanted a range of numbers between 0 and 1 in 0.001 steps, I would just let range go in thousands and then divide by 1,000, and then I get thousands as steps, right? So this is just a little trick to produce these numbers. I show you how it works now. Let's execute it, and you will see if I execute it, it takes a second, right, always to begin. And then here is my list. Down here, you can see the list with all the numbers that I have produced. Now I want to define two simple functions that will show different properties of functions. One will be linear, one will be not linear. And this is what I'm doing here. Output's linear, and I just produce the values. I don't even bother to make a function now in Python because I just want to plot them once. So I will produce the values that I want, put them in a list, and then display the list. So I want the outputs for x in inputs, right? I make a loop over my inputs, and you remember my inputs are here, is this area of inputs here. I want for x in inputs, I have the linear output empty list, which I created, and I append to it x, which is my input value, plus 3. So this function just adds 3 to every input number. And I have a second number which squares the input. So I have the output squared, and then for every x in inputs, my output square appends x squared. And these two stars here are the power function in Python. Squaring, putting to the power of 2 is star star 2. Okay, and now I'm ready to plot. And if you don't remember how to plot stuff, go please back to our previous course where we did matplotlib and we explained in detail how this works. So here I have a size of my whole figure. I will actually reduce this a little bit because I'm afraid it's too big to display here in this recording nicely. And I will plot two of them, right? You see I have plot the linear function first and then plot the squaring function, so I get two different figures. And in every plot I have the inputs here, I have my outputs, I have my color and the width of the line, and then I have a few labels and I plot this. So let's just do it, the linear and the squared. And you see first is the linear, add 3 to everything. Looks like this is one line. And why is the line like this? Because if I add 3 to everything, then y is x plus 3. So essentially y is x and something. If y was like x without anything, if I was just identical with x, I would have a line going through 0 where every y is the same as the x. So at 1x it would be 1y, at 2x would be 2y, 3x would be 3y. So it would be a 45-degree line going up. But now I also add 3, and this means I shift my whole line up, and I get it up here 3 points up on my diagram. Here's the 3, right? And for every value of x, I get 3 more in the y. So for 2, I get 5. For 4, I get 7, and so on. So this is what I expect here, right? And then I look at my other function, which is the square function, and you see this has a totally different way of looking, like this. And what happens here is that now if I have 0, of course it's still 0, but if I have 1, it's 1. If I have 2, it's 2 squared. It's actually 4 right here. And if I have 3, it's 3 squared. It's 9. And if I have 4, it's 16, and so on. So this grows very fast. At 5, I'm already at 25. At 6, I'm at 36. At 9, I'm at 81. At 10, I'm at 100. So this grows and becomes steeper and steeper, right? And so with very small steps on the x-axis, I'm jumping big amounts on the y-axis. And this is the difference you have to see between these two functions. The first one is a very calm function. It's directly proportional. However much I go on the x-axis, I also go on the y-axis. It's very predictable. It's very easy to see what it does. It doesn't do anything surprising. The second one, the nonlinear function, begins in a similar way, very easily and calmly, but very quickly it jumps very fast. It becomes faster and faster, and it totally goes out of control. If this was a physical process, it would be like an explosion. Everything reacts suddenly more and more and more, and it becomes a runaway process. This is what I have here with my square function. It's still predictable, but it becomes really difficult to predict the exact value without calculating it. I cannot do this easily. So let's say it was 958. Where am I? How much is it? It's a lot, right? If I square this. But it's difficult to guess. At some point, we're not good at squaring things in our mind. It's not as easy as adding 3, right? So this is a function that grows very quickly. In terms of natural processes, analogies for what these functions represent, a linear growth of something would be, let's say my probability, I don't know if this is true, right? But it came up as an example in my class, so let's assume it's true. My probability of getting cancer from smoking plotted against the cigarettes I smoke every day. So the more cigarettes I smoke, the more probability I have to get cancer from it. And the fewer cigarettes I have, the less is my probability for cancer. Now again, it's not a statement about medicine here, it's just a visualization of what I mean by a linear function. So I may be totally wrong about that. Another linear function, the amount of money I spend and the amount of money that is left in my pocket are linear, right? I give $3 away, then I have $3 less in my pocket. If I plot them, it will be a falling function, right? The amount in my pocket, but it will be linear to my spend. It will be a straight line. The squaring function is more like what we expect from compounding interest, for example, right? You have $2 in the bank, and in a year you have 4, and if you leave them in the bank, in another year you have 8, and in another year you have 16 and 32, and so this keeps doubling, right? So it gets more and more. This is an example of a square function. And of course, these nonlinear functions are also in populations. You have 2 people making 4 children, and then each of these 4 children makes another 4 children. So in the next generation, I have 16 children and so on. And so very quickly the population grows. This is what bacteria do, for example, in a dish. So this is why when you leave something out that can grow bacteria, you must be very careful, because it is very easy for that to get out of control. And if you leave a food out, in the first hour, you will not notice any difference. In the second hour, you will not notice any difference. Perhaps after 5 hours, if it's warm enough. If it is a dish of milk, for example, you will notice that the milk is starting to go bad, but then suddenly the milk will totally rot. And this will happen relatively suddenly because it's a nonlinear function. The bacteria have doubled and doubled and doubled, and at some point they're doubling so fast that the milk just rots immediately. And you may be missing the exact point. The next time you look at it, it's already gone. So this is square growth, and this is also population growth. If we have enough resources and no space restrictions and no resources restrictions, then this is also how populations grow. Okay, here is a visualization as values, because some people can see it better by seeing the diagram, but some learners are not happy with diagrams. It's difficult for them to interpret the diagram. They are happier seeing the numbers. So here I also gave you the numbers. For the x+3 function, you have the input and the output. You can see how this works. For the squaring function, you have the input and the output. This is called a function machine, where you have the different inputs one by one and you show the mapping to the output. And so just this another representation is the same thing but be plotted, but instead of being plotted now, it's the values. So why does this matter? Now we said it already, what is the difference between linear and nonlinear? It's just how surprising the growth is, how violent it is. Linear function grows slowly, it's predictable, it's easy to handle, it doesn't surprise us, it's a process we can easily control. If it's something growing linearly, I can intervene, I can slow its growth, I can accelerate its growth. A function that grows non-linearly, and especially if it grows exponentially, like the one we saw, will suddenly become faster and faster and faster so that it feels like it's exploding, and it becomes very difficult to control. I cannot easily control a nuclear explosion, for example, because a nuclear explosion is an exponential growth function where more and more of these atoms react with each other, and the more react, the more they produce other products, neutrons, electrons, whatever it is, and these react with more things. And so this whole chain reaction goes under control and becomes an atomic bomb, right? This is exactly the point of a nonlinear growth, of an exponential growth. And finally, here you have a visual for three types of growth. There are many kinds of growth, right? The linear growth is always the same kind of thing, but then you have many types of nonlinear growth. It can be accelerating, like we just saw, the quadratic equation, or it can be logarithmic, a decelerating growth, a growth towards a saturation value, right? This is, for example, what your feeling of being full does while you're eating. So in the beginning, you're very hungry, and with the first bite of your food, you feel very good. Your feeling of being not hungry anymore increases very fast, right? The opposite of being hungry. And with the next bite, it's a little less. With the next bite, it's a little less. At some point, eating more and more food doesn't make you less hungry. It just stays there, and you cannot actually eat more food. Another example for a process like this that slows decelerating growth would be you put a heater in a cold room and let it run. Although the heater is emitting heat constantly, it will never increase the temperature of the room to an extent that the room melts down, right? What will happen is at the beginning, the room temperature will very fast increase because the heater makes a big difference when the room is very cold. But then as the room temperature increases, the heater will have less and less of an effect. And then at some point, the room will be losing heat through the windows, through the door, through the walls, at a rate that is the same rate at which the heater manages to heat it. And then the room temperature will not grow at all anymore. It will be at an equilibrium. So if you put a heater in a big room, it will heat the room to 20 degrees, 30 degrees, whatever it is, and then it will stop heating. It will still run, but it will not heat it anymore. It will just maintain the heat at this point of equilibrium where the lost heat is equal to the heat that the heater emits. And then you have the saturation curve, which looks exactly like this here, the logarithmic curve. The nice thing with Python is that we can do this, we can try these things out, you can change the values, you can see what they look like. Just go to this code here, and I will put the code in the lecture notes, which we will also find somewhere. I will put down a link where they are, and then you can go and find it there and try out yourself, change the values. Okay, that's it for the moment. Let's stop here, and in the next chapter we will talk more about very badly behaving functions and why these are particularly interesting. See you there.